end, that I erased the name, is called telomerase. It can increase these repeat sequences to restore the length after replication. Here's the enzyme here represented by this green, whatever you want to call that shape. And actually this enzyme, telomerase, it's a type of enzyme that has a name. It's called, telomerase so you know I can read it. It's a type of enzyme known as a reverse transcriptase. Have you ever heard of this enzyme? I don't think I've talked about it. I'll tell you a cell that has this enzyme. Actually, it's not a cell. Let me back up. I said something very bad. It's not a cell. It's a virus. That virus is called HIV. You ever heard of HIV? HIV is an RNA virus, but infects your cells. If you're that unlucky, affects one of your CD4 T cells. It will take its RNA viral genome and reverse transcribe it to DNA. Remember transcription, we're going to learn about. Transcription is going from, that's chapter 15, when you go from DNA to RNA, that's called transcription. Because as we'll see, you're making an RNA transcript of the gene to use as a working copy of the gene. It's not really a copy, a working sort of a negative of the gene to direct protein synthesis. So if you go in this direction, that's reverse transcription. Okay? And that's what happens here. It turns out that the telomerase enzyme is part protein, and it has a single-stranded RNA template. That's what the blue line is here. RNA. And it uses this sequence, and this sequence is complementary to this. So it have the RNA molecule, this enzyme would have this base pairs. That sequence, okay? And so it attaches to the end, the 3' end of the lagging strand, and it extends it, it grows it. So notice it grows it back out, making DNA from the RNA template, so it's reverse transcription. Then a primer can be attached and it can be mostly restored. This solves the end replication problem in eukaryotic chromosomes. The lagging strand end cannot be replicated. Does that make sense? Well, let me draw a picture then, okay? And I think I can use one color here. So let me make 5', 3'. Here's my replication fork here. Okay. So remember, they have new copies being made according to base the anti-parallel nature. So here's the solid line is the primer. Okay, and this has to be anti-parallel to this end. Okay, so there's one primer in the new strand. Another primer was there. Okay, arrow is the 3' end, just so you get that. Okay, right. Of course, this is the leading strand. Okay, and it's being synthesized continually into the replication fork. Right. Okay. You put the 3' near the arrow, so you don't label it here. So it just goes continuously. Okay, that's now time. You've heard of time. Okay, let's complete the replication here. So the fork has reached the end here. Okay. So here's the new replicate. Okay, all the way there. Okay. This is not the end of the chromosome. It's further in that way. Because at this other end would be a lagging strand that way. But let's not worry about that right now. Maybe I'll just leave it like that. Well, that's okay. Like 3'. And here's the lagging strand was produced like this. We had a primer here. Another primer here. Right? And the last primer was put right there. Okay? Okay? So what happens then when the primer is degraded, okay, this is the 5' end here, I can't synthesize new one in that direction. Okay? Right? So we got this gap here created. Okay? because the 3 direction, because it wants to go that direction, but I can't fit it. I'll move the primer out, and there's a gap here. I can't fit. I need a primer here to take it that way. So what do? We just throw this in further out. We can prime it and then seal it. That's what this enzyme does. It's part protein, part RNA. It's got a sequence complementary to the telomeres, and it can, the reverse transcription, extend this. Then you can prime it and then seal it back. And it can restore chromosome to full length. And that happens in your germ cells. So the eggs and sperm you make, ladies and gentlemen, respectively, they get full set chromosomes. But an embryo is dividing rapidly. So that means, let me back up. That means that in the germ tissues, this enzyme is being expressed. It's on and active. It's in all your cells. It's just a gene that's never turned on in the rest of your body cells. It's active in germ tissue. It's active in early embryo division. And it's also active in cancer cells. That's why cancer cells are immortal. They keep this enzyme active, and they can continue to, every cell division, restore the full-length chromosome, and they'll divide as long as you feed them forever. Whereas most cells, most of your body cells, most of the somatic cells, this enzyme is off, and with every chromosome, so it means as your cells divide, this is not working, so the ends get shorter and shorter and shorter and shorter. And after 50 to 60 cell divisions, the cells enter what's called replicative cell senescence. Also known as the Hayflick limit, by the guy that described it. Which means roughly like 50 to 70 cell divisions for a typical body cell, and the telomeres are so shortened, it's not dividing anymore. It is kind of a safeguard against runaway cell division, sort of. Except in tumors, for some reason, in many tumors, a great majority of tumors, this enzyme becomes activated again. So they can divide, and never stop. So there's been a big research effort to turn that enzyme off in tumors. They would divide at a certain stage and then they can't divide anymore. There was a company in Palo Alto called Geron. Okay. They were doing 2 cool things. One thing was actually it's still in clinical trials, they've got an anti-telomerase therapeutic. It works in some tumors. So they've survived as a company. They were on the brink of bankruptcy. But their anti-telomerase ingredient does tend to disable this enzyme in tumors, and they divide and then they can't divide anymore. That's a good thing. The other thing Geron was doing is they were able to, they had some substances they were able to actually restore a spinal cord break. Like they could sever a spinal cord in mice, and then with their treatment, it would restore it, and they could walk again. That hasn't worked out in clinical trials so far, so I think that research was farmed out to somebody else, and I think that work is still happening. So that would be a great thing in the near future. You could restore spinal cord breaks like that in people that have lost mobility and are wheelchair bound with recovered mobility. So that's coming. That's coming as they understand sort of the nature, the difference in the neural environment of the central nervous system versus peripheral nerves. Because peripheral nerves, you cut and burn them, they regrow. Central nerves don't for some reason. But they were starting to figure out how to get it. They almost went bankrupt. I know because I own stock in the company, and I'm letting that stock ride all the way. You know, if stock goes down, I'm not a big stock guy, but if stock goes down, you say you're a loser for sure. But I figure I'm just going to ride all the way to the grave, and maybe I get lucky. So I know their anti-telomerase enzymes working because they're still surviving somehow. I look at their stock is, I bought it at 20, it's like down to 3. So it's like, whoa, shit, that was a good investment. That was after I sold my Apple stock. Why did I sell my Apple? Okay. So, interesting story here about the unreplicated problem and how understanding it might help to defeat certain cancers, many types of cancer. Make sense? Okay. Now let's talk about mistakes in replication and how they're corrected. and some of the other repair mechanisms of DNA to complete this chapter. Then we're going to jump into chapter 15. I know we're way behind this syllabus, but that's okay. So, DNA polymerases make mistakes. Okay? I think it's about 1 in every 10,000 nucleotides or so, the wrong base is added. So it's a pretty high mutation rate. It would be incredibly high if it weren't corrected. It would be so high that probably multicellular life could not have evolved. But we're not corrected. But there is a correction because the DNA polymerases, we know that when they synthesize the complement strand, we talked about this already, that goes in the 5' to 3' direction. But the main synthesizing enzyme, remember that's DNA polymerase 3, okay, it also has, we say, exonuclease activity in the opposite direction, in the 3 to 5 direction. Exonuclease. Exo means outside of the end. Nuclease is an enzyme that eats nucleotides. Like a protease is an enzyme that digests proteins. Okay, a lipase digests lipids. Okay, nucleases digest nucleotides. This is one that works at the end of a nucleotide chain. So, check out from your book. So here we see, here's DNA polymerase 3. There's this clamp, ring clamp. A is entering the active site. It should add a T, but it added a C by mistake. Okay, it stops. It's going in the 5 to 3 direction of the strand. It backs up, chews it out in the 3 to 5 direction, and then it can add the right base and continue on. And that dramatically reduces the mutation rate. Okay? So